Welcome geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Let's now look at how to express sine 6 theta over sine theta in terms of cos theta. So sine 6 theta again is the imaginary part of cos 6 theta plus I sine 6 theta. We apply the Nimborist theorem and expand it using binomials theorem. Now, we cancel out all the real parts and we obtain 6c to the power of 5 times s minus 20c cubed times s cubed plus 6c times s to the power of 5. Now we divide this expression by sine theta. And we obtain 6c to the power of 5 minus 20c cubed s squared plus 6c s to the power of 4. And we are going to convert all the s into c because it wants us to express it in terms of cos theta. Simplifying this expression, we obtain 6 cos theta minus 32 cos cubed theta plus 32 cos theta to the power of 5. In the next few examples, we are going to express power of sine theta and cos theta in terms of multiple angles. So, in this example, we want to show that sine theta to the power of 6 is equivalent to 1 over 32 times 10 minus 15 cos 2 theta plus 6 cos 4 theta minus cos 6 theta. So, we first let z equals to cos theta plus I sine theta, while z star, its conjugate, equals to cos theta minus I sine theta. So z minus z star, if you see closely, we obtain 2I sine theta. Whereas if you add them together, you obtain 2 cos theta. But in this case, we want sine theta, so we are going to minus them. So z minus z star is 2I sine theta. But then we want sine theta to the power of 6, so we change it z minus z star to the power 6 equals to 2i sine theta to the power 6. And so we have 64i to the power 6 times sine theta to the power 6. And we shift the 64i to the power 6 to the other side. So we have sine 6 theta. And this is equivalent to negative of 1 over 2 times z minus z star to the power 6. And then we know that, and we convert z star into z to the power of negative 1 using the De Moivre's theorem. The next step is to expand the whole thing using the binomials theorem. Now we are going to pair all the similar numbers up. For example, z to the power of 6 and z to the power of negative 6, z to the power of 4 and z to the power of negative 4, z squared plus z to the power of negative 2. Remember that initially we let z equals to cos theta plus I sine theta. If we have z to the power of 6, that means using the De Moivre's theorem, it is equivalent to cos theta plus I sine theta to the power of 6, and then cos 6 theta plus I sine 6 theta. And that applies to z star as well. So we have z to the power of minus 6, and hence z to the power of 6 plus z to the power of minus 6 is equivalent to 2 cos 6 theta. For z to the power of 4 plus z to the power of minus 4 is 2 cos 4 theta. And z to the power of 2 plus z to the power of minus 2 is 2 cos 2 theta. So remember, when you see a plus, it's going to change it into a cos. And finally, we simplify this expression and we can obtain the answer. Next, we are going to show that cos theta to the power of 5 equals to 1 over 16 times cos 5 theta plus 5 cos 3 theta plus 10 cos theta. Using z equals to cos theta plus I sine theta and z star equals to cos theta minus I sine theta, we have cos theta to the power of 5 equals to 1 over 2 times z plus z star to the power of 5. And we convert the z star into z to the power of minus 1 again, and expand the whole expression using binomials theorem. And then we are going to arrange the similar powers together. So z to the power of 5 and z to the power of negative 5, so on and so forth. And then now we are going to convert z to the power of 5 plus z to the power of negative 5 into 2 cos 5 theta, whereas z to the power of 3 plus z to the power of negative 3 is 2 cos 3 theta, and then 2 cos theta for the last one. And then we simplify this expression and we obtain the answer. In the last example, we are going to prove the sine theta to the power of 5 identity. So in this case, we are going to write I to the power of 5 times sine theta to the power of 5 equals to 1 over 2 times z minus z star to the power of 5. And then convert z star again into z to the power of -1. And then expand it using the binomials theorem. And then you rearrange the similar power together. And in this case, we have z to the power of 5 minus z to the power of -5. And since we are going to minus it and not plus it, the minus sign indicates is a sign. So z to the power of 5 minus z to the power of -5 is 2i sine 5 theta. And z to the power of 3 minus z to the power of -3 is 2i sine 3 theta. And the final one is 2i sine theta. So this is something that you need to memorize. And finally, we are going to remove the I and remove it to the other side. So I divided by I to the power of 5, and we have I to the power of 4, which is 1. And we further simplify it by factorizing the 2 out, and we obtain the answer. Now, let us look at how to find the solution of equations of the form z to the power of n equals to 1, where z is a complex number. So let us consider the first case, when n equals to 3. We will have z cubed equals to 1. So rearranging it, we have z cubed minus 1 equals to 0. And then we factorize it. So we have z minus 1 times z squared plus z plus 1 equals to 0. And finding the roots, we have z equals to 1, and the other one we use the quadratic formula to solve, and we obtain a complex expression for the other two roots, which are themselves a pair of conjugates. So we have z equals to minus 1 over 2 plus minus root 3 over 2i. However, the equation above can be solved using De Moivre's theorem in the manner described below. So we have z cubed equals to 1. And we know that 1 is cos 2 pi, or any cos 2k pi where k is a positive integer, say 0, 1, 2, 3, 4. And then sine 2k pi is a 0. So cos 2k pi plus I sine 2k pi is still equals to 1. And then we use De Moivre's theorem, changing it into cos 2k pi over 3 plus I sine 2k pi over 3, where k equals to 0, 1, 2. So if it is the power of 3, it means the k has got 3 values, and we start from 0. So this gives z equals to 1, or minus 1 over 2 plus minus root 3 over 2i, which agrees with the solutions above. What about negative 1? So we know that negative 1 equals to negative 1 times 1. And negative 1 is cos pi. So sine pi is still 0, so cos pi plus I sine pi times cos 2k pi plus I sine 2k pi, which is equivalent to cos 2k plus 1 pi plus I sine 2k plus 1 pi. Thus, we find the solution to z cubed plus 1 equals to 0 as follows. So we have z cubed plus 1 equals to 0, and then moving plus 1 to the other side, we have z cubed equals to negative 1. And z cubed also equals to negative 1 times 1, which is cos pi plus I sine pi times cos 2k pi plus I sine 2k pi. And hence, cos 2k plus 1 pi plus I sine 2k plus 1 pi. Using De Moivre's theorem, we divide it by 3, and then we get cos 2k plus 1 pi over 3 plus I sine 2k plus 1 pi over 3, where k equals to negative 1, 0, and 1. Remember, they must have 3 values because it is power 3, and any numbers in ascending orders. So the 3 roots are cos negative pi over 3 plus I sine negative pi over 3, cos pi over 3 plus I sine pi over 3, and cos pi plus I sine pi. So these 3 roots, when you plug them into the calculator, you get a more simplified expression, 1 over 2 plus minus root 3 over 2i and negative 1. So, as you can see, the root occurs in conjugate pairs. Let us now look at this example. We want to find all the solutions to the equation z to the power of 5 equals to 32. So the first step is to write z to the power of 5 equals to 32 times 1. And we know that 1 is cos 2k pi plus I sine 2k pi. And using the De Moivre's theorem, we divide this by 5, and we have z times 2 times cos 2k pi over 5 plus I sine 2k pi over 5. And now the k must have 5 values. So in this case, we have minus 2, minus 1, 0, 1, 2. Remember to put the numbers in ascending order. Now we substitute all the k value and we obtain 2 cis negative 4 pi over 5, 2 cis negative 2 pi over 5, 2 cis 0, 2 cis 2 pi over 5, and 2 cis 4 pi over 5, where cis is cos something plus I sine something.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.